Okay, I'd like to thank the organizers for inviting me. It's a very interesting venue. This is going to be a sudden grinding change of gears from everything that's happened so far. You'll see this has quite a different character, and I'll make some probably very contentious claims, and hopefully we'll have some time to talk about them. So let me go to the beginning. What is physics after all, which turns out to be a much more contentious question than it ought to be. It used to be, when I was a sprat, that you'd hear things like this, that physics is the theory of matter in motion, which gives you a nice flavor for the thing. It tells you it's awfully universal. It tells you that all biological systems are also physical systems because whatever else they are, they're matter in motion and so on. But you could object to it. You might say that it's not really clear that everything that's physical should count as matter. Things you think of as physically real are, suppose you believe there are quantum states. So I mean, I said quantum mechanical wave functions there, but quantum states, something that corresponds to the wave function, are real. Do you want to say they're material? The word matter is a little vague here. And it's not quite clear that the only things these entities do is move. So if you were Democritus and you thought all there were shaped atoms bouncing around in the void, you're pretty well covered with this definition. But you might say there are changes that don't really count as motions. So you could update this thing a little bit to be a little safer, that physics is the theory of what space-time, entities in space-time, which is what Bell would call the local beables of the theory, and entities that interact with them are, and what they do. So the main bumper sticker is physics should tell you what there is and what it does. Now, what we practice, as everybody now knows at the end of today, is mathematical physics. So what's that? It's physics that uses mathematical structures as representations for physical entities and physical states. I take that to be a fairly uncontentious definition. It's really important to think about this a lot. That is, the role of mathematics in physics is the medium of representation, the way that natural language is the medium of representation in novel writing. Or in history, to be, hopefully we're doing something more than writing novels. So say if I'm a historian. And the problem here, and this is an absolutely endemic problem to try and even talk about these issues, is that systematically the language has been run together. The language describing the mathematical objects, which are abstract, and the language that's supposed to be about the physical things, which are not abstract. So for example, I'm going to give you 3 sentences which I think anyone who knows this kind of stuff could hear and not feel at all worried about any of the 3 sentences. So you're looking at an experiment and you say, the electron reacted to the electric potential. And then someone says, hey, what is an electric potential anyway? And they say, the electric potential, that's a scalar field. And being an annoying person, they say, what's a scalar field? And you say, a scalar field is an assignment of real numbers to space-time points. And then you sort of run those 3 together and you say, wait a minute, the electron just moved because it interacted with an assignment of numbers to space-time points. And that's not right. That makes no sense at all. Nothing is going to get deflected by an assignment of numbers to anything. So what's the problem here, right? This is the kind of thing, as a philosopher, your ear becomes very highly attuned to. The term scalar field is so ambiguous between the mathematical thing, which is an assignment, it's a function, right? It's an assignment of numbers to something, and to scalars, right, which are numbers to something, and the thing it's supposed to represent, which is presumably not an assignment of numbers to anything, that I don't know what scalar field means, right? I can't say that one of those meanings dominates over the other. This happens, by the way, in spades in quantum mechanics with the wave function. People ask, is the wave function real? And again, you have two things. You have a function, which is obviously a mathematical thing that we call the wave function. And then there's an open question whether there's a physical thing that it is supposed to represent. I prefer to call that the quantum state. So often the discussion about is the wave function real, in my terminology, you have a perfectly good question like, is there a quantum state after all? But if you're using the word ambiguously between the math and the thing the math is supposed to represent, the conversations can easily become very confused. What's the structure, according to me, and man, is this an unpopular definition, of a proper physical theory? It should be clear, and if we want a clear and unambiguous physical theory, is not simply a mathematical formalism, right? A piece of mathematics is, whatever it is a piece of mathematics. And that's it. It's not a physical theory of anything. If I give you a mathematical formalism and I add to it rules that tell you how to use it to make predictions, that also, according to me, is not a physical theory. It's a kind of prediction-making recipe. And it may be good, it may work well, it may work poorly. If you think about the Osiander's preface to De Revolutionibus, when he's sort of presenting the Copernican theory, he was very explicitly being instrumentalist about that theory, saying, do not take it seriously, right? Don't think that I'm giving you a story about what's really going on. I'm giving you a way to calculate, make predictions in positional astronomy. It may be simpler and more accurate than the one you've been using. I am not saying the Earth is actually rotating on its axis. I am not saying that the Earth is actually orbiting the sun. Of course, Copernicus was saying exactly that, but Osiander was trying to keep him out of trouble. That's what it is to be an instrumentalist about a theory. But Copernicus really had a theory, right? The theory was not just the predictive apparatus. What was the theory? Well, the theory, the Copernican theory, gives you as clear as you can, precise physical theory is a mathematical formalism together with what I'll call a commentary on the formalism. And what's in the commentary? So I'm going to make a little suggestion here, which no one is ever going to adopt, but I'll show you why it might be a useful suggestion, about how to put the commentary on the mathematical formalism into what I'll call a canonical form. Just a structure that you can take any physical theory you want to talk about, any theory of mathematical physics you want to talk about, and just put the commentary on it into this structure, and it helps make clear what the theory really is. So what's the commentary supposed to do? It's supposed to specify, first of all, the fundamental non-derivative ontology of the theory. Okay? So that is, what does the theory postulate to exist? And it's not an accident that John Bell invented the word beable, which is just the Anglicization of ontology, right? Ta onta are the things that exist. And so he took be, right, the things that are. So the beables, what Bell meant by the beables of a theory is just what we normally mean by the ontology of the theory. So you should tell you, what does your theory postulate to exist? This is also a bit like Detlef Durr's question, what is your theory about? When you do that, you could at the same time give a general account of what kinds of things these are. So you might make a distinction, as Bell does, between local beables and non-local beables, right? Where the local beables, in some sense, are elements that exist in small and restricted regions of space-time, and the non-local beables, if any, are things that don't. Like, if there's a quantum state, if there is a physical thing that corresponds that the wave function is representing, it's not a local thing. It should specify which of the mathematical entities that are in your formalism are going to be used to represent that fundamental ontology. At this point, you could add some purely mathematical remarks about the mathematical structure being used, and we'll have an example of that in what we're going to run through. It should contain, and this is a brand new word I just made up, a nomology from nomos, from law, right? So just as you want the ontology is your account of what exists physically, the nomology is what is the account of the laws, the fundamental physical laws that you're postulating. There's a connection between the ontology and the nomology, which is that the laws should be stated mathematically only in those mathematical terms that you've already told us represent the fundamental ontology. And it's at this point that a bunch of the main force of Bell's against measurement and the main force of people saying there is a measurement problem arises because measurements are not fundamental physical things. They may be physical things, right? A measurement, you might say, is just a physical interaction of a certain kind. That's fine. A chair, right, is a physical thing, but it is not a fundamental physical thing. It is a composite physical thing. And so the word chair should not appear in the laws of physics. You would be in a lot of trouble if the word chair appeared in the laws of physics, because you take a chair and you start chipping away at it bit by bit, and like Theseus's boat, at some point it ceases to be a chair. But there is no particular point where that happens, and if the laws of physics depended on whether it was a chair or not, they wouldn't know what to do, right? And if the laws of physics had to know whether a measurement was being performed in order to know whether it should collapse the wave function or continue a nice linear evolution, the laws of physics will not know what to do, because there are all kinds of physical interactions that are neither obviously measurement enough like or not measurement enough like to count as measurements. That's why Bell against measurement was against, it's against the word, right? Against, quote, measurement. And not even as a bad word in itself, but not as a word that should appear, as Bell said, in a formulation of a professionally precise physics. And he had a lot of other words, microscopic, macroscopic, reversible, irreversible, a lot of words that he says are not sufficiently sharp to appear in the statement of a fundamental physical theory. Good. So if you did it this way, that you had to first tell me what you're saying exists at a fundamental level physically, and then only write the laws in terms of that stuff, you never would have had the measurement problem, because nobody ever would have attempted to write laws that had the word measurement in them.